Question 1. The performance metrics show a consistent increase in packet loss and latency on a critical WAN link connecting two enterprise branch offices. The network administrator suspects a routing issue, but is unsure of the most effective initial troubleshooting steps. Option A. Focus exclusively on analyzing the routing protocol's convergence time and neighbor adjacencies. Option B. Immediately initiate a hardware replacement of the WAN router at one of the branch offices. Option C. Verify the WAN interface status, check the routing table for accurate next hop information, and confirm the quality of service (QoS) configuration is correctly applied and functioning. Option D. Randomly adjust quality of service (QoS) parameters on the WAN link to see if it resolves the issue. Correct answer is C. Verify the WAN interface status, check the routing table for accurate next hop information, and confirm the quality of service (QoS) configuration is correctly applied and functioning. Explanation. The performance metrics show a consistent increase in packet loss and latency on a critical WAN link connecting two enterprise branch offices. This scenario is professionally challenging because network engineers must quickly diagnose and resolve the issue to maintain business continuity and avoid service disruptions. The urgency of the situation, coupled with the potential impact on critical applications, demands a systematic and informed approach to troubleshooting. The chosen solution must not only address the technical problem, but also adhere to established best practices and any relevant Cisco guidelines for enterprise network management, as implied by the exam's focus. The correct approach involves a methodical investigation of the WAN link's underlying technologies and configurations. This includes verifying the operational status of the WAN interfaces, examining the routing protocols for any convergence issues or suboptimal path selection, and scrutinizing the quality of service (QoS) configurations to ensure traffic is being prioritized correctly. Specifically, verifying the encapsulation and physical layer status of the WAN interface, checking the routing table for accurate next hop information, and confirming that QoS policies are applied and functioning as intended are crucial steps. This systematic verification aligns with Cisco's recommended troubleshooting methodologies for advanced routing and services, emphasizing a layered approach to problem resolution. Adhering to these established practices ensures that the root cause is identified efficiently and that the implemented solution is robust and sustainable, minimizing the risk of recurrence. An incorrect approach would be to immediately assume a hardware failure and initiate a costly replacement without proper diagnosis. This fails to follow a logical troubleshooting process and wastes valuable resources. Ethically, this could be seen as unprofessional due to the lack of due diligence. Another incorrect approach would be to arbitrarily adjust QoS parameters without understanding the current configuration or the impact of such changes. This could inadvertently worsen the problem or negatively affect other traffic flows, demonstrating a lack of technical understanding and potentially violating best practices for network service assurance. A third incorrect approach might be to focus solely on the routing protocol without considering other potential causes like physical layer issues or congestion. This narrow focus can lead to a prolonged outage and a failure to identify the true root cause. Professionals should employ a decision-making framework that prioritizes systematic troubleshooting. This involves 1. Gathering comprehensive data, performance metrics, logs, configurations. 2. Forming hypotheses based on the data. 3. Testing hypotheses through verification and targeted configuration checks. 4. Implementing solutions based on confirmed root causes. 5. Validating the solution and monitoring for recurrence. This structured approach, aligned with industry best practices and vendor-specific methodologies, ensures efficient problem resolution and minimizes business impact. Question 2. During the evaluation of a critical security vulnerability impacting a core routing platform, a network engineer identifies a vendor-provided patch. The engineer is concerned that applying the patch directly to the production environment might introduce unforeseen network instability or performance issues, potentially disrupting critical business operations. The engineer has access to a lab environment that closely mirrors the production setup. What is the most professional and risk-averse approach to address this situation? Option A. Immediately apply the patch to the production environment to mitigate the security risk as quickly as possible, assuming the vendor's patch is thoroughly tested. Option B. Apply the patch to a subset of non-critical production devices first to gauge its impact before a full rollout. Option C. Thoroughly test the patch in the lab environment to simulate production conditions and identify potential issues before scheduling and implementing the change in production, including a rollback plan. Option D. Defer the patch deployment indefinitely, citing the potential for network disruption and the low likelihood of the vulnerability being exploited in the current network configuration. The correct answer is C. Thoroughly test the patch in the lab environment to simulate production conditions and identify potential issues before scheduling and implementing the change in production, including a rollback plan. Explanation: this scenario presents a professional challenge because it requires a network engineer to balance the immediate need for network stability and performance with the long-term implications of a security vulnerability. The engineer must make a decision that minimizes risk to the organization's operations and data, while also adhering to established security protocols and best practices. The complexity arises from the potential for a misconfiguration to cause widespread outages or introduce further security risks, necessitating a thorough understanding of the technology and its operational impact. The correct approach represents best professional practice because it prioritizes a controlled and validated deployment of a critical security patch. This involves thorough testing in a lab environment to simulate production conditions and identify any potential conflicts or adverse effects before implementation. This methodical approach minimizes the risk of unintended consequences, such as service disruptions or performance degradation, which could have significant operational and financial repercussions for the enterprise. Adhering to a change management process, which typically includes rollback plans, further reinforces this best practice by ensuring a swift return to a stable state if issues arise. This aligns with general IT governance principles that emphasize risk mitigation and service continuity. An incorrect approach that involves immediately applying the patch to the production environment without prior testing is professionally unacceptable due to several regulatory and ethical failures. Such an action disregards the principle of due diligence, which mandates that professionals take reasonable steps to ensure the safety and reliability of systems under their care. It also violates the implicit ethical obligation to protect the organization's assets and operations from harm. From a compliance perspective, depending on the industry, this could lead to breaches of data protection regulations if the patch causes data corruption or unavailability. Furthermore, it bypasses established change control procedures, which are often mandated by internal policies and sometimes by external regulatory bodies to ensure accountability and auditability of network changes. Another incorrect approach, which is to ignore the vulnerability due to the perceived low risk and potential for disruption, is also professionally unsound. This demonstrates a failure to proactively manage security risks. Organizations have a responsibility to protect their networks and data from known threats. Ignoring a known vulnerability, even if the immediate impact is uncertain, exposes the organization to potential future exploitation, which could lead to significant security incidents, reputational damage, and regulatory penalties. This inaction can be seen as a dereliction of professional duty. A professional decision-making process for similar situations should involve a structured risk assessment. This includes identifying the vulnerability, understanding its potential impact, evaluating the proposed solution, the patch, and assessing the risks associated with implementing the solution. A key step is to consult and adhere to the organization's established change management policies and procedures. This typically involves creating a detailed implementation plan, including testing, rollback procedures, and communication strategies. Collaboration with relevant stakeholders, such as security teams and operations management, is also crucial to ensure a comprehensive understanding of the risks and to gain necessary approvals. The decision should always prioritize the stability and security of the production environment, even if it means a slight delay in patch deployment. Question 3. Market research demonstrates that a critical enterprise application is intermittently unavailable to users across multiple branch offices. Network monitoring indicates that connectivity to the application server is intermittently lost, but the core network infrastructure appears stable. A network engineer is tasked with resolving this issue. Which of the following approaches represents the most effective and professional method for diagnosing and resolving the problem? Option A. Proceed to roll back the most recent configuration changes made to the core routers, as these are often the source of intermittent connectivity problems. Option B. Immediately assume a complex BGP route manipulation issue and start analyzing BGP neighbor states and path attributes. Option C. Focus troubleshooting efforts on the application server's operating system and firewall logs, as the issue is likely application-specific. Option D. Begin by verifying physical layer connectivity, IP addressing, and routing protocol adjacencies between the branch offices and the data center where the application server resides. The correct answer is D. Begin by verifying physical layer connectivity, IP addressing, and routing protocol adjacencies between the branch offices and the data center where the application server resides. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise networking where a critical service outage impacts business operations. The challenge lies in rapidly identifying the root cause and implementing a solution while adhering to established operational procedures and potentially service-level agreements, SLAs. The pressure to restore service quickly can lead to hasty decisions, potentially exacerbating the problem or violating security and operational best practices. The need for a structured, methodical approach is paramount to ensure effective troubleshooting and minimize future occurrences. Correct approach analysis. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most fundamental aspects of the network and progressively moving to more complex configurations. This aligns with best practices for network diagnostics and aligns with the principles of implementing robust and reliable enterprise routing and services. By verifying physical connectivity, IP addressing, and routing protocol adjacencies first, one addresses the most common failure points. This methodical approach ensures that basic network functions are operational before investigating more intricate issues, thereby preventing wasted effort and potential misdiagnosis. This is considered best professional practice as it is efficient, effective, and minimizes the risk of introducing new problems. Incorrect approach is analysis. One incorrect approach involves immediately assuming a complex configuration issue, such as a BGP route flapping or an OSPF area misconfiguration, without verifying the foundational elements. This is professionally unacceptable because it bypasses essential diagnostic steps, leading to inefficient troubleshooting and a higher probability of overlooking simple, yet critical, problems. It can also lead to unnecessary configuration changes on complex protocols, potentially destabilizing other parts of the network. Another incorrect approach is to immediately revert to a previous known good configuration without a thorough analysis of the current state. A reverting can sometimes be a quick fix. Doing so without understanding the cause of the failure means the underlying issue remains unaddressed and is likely to recur. This is professionally unsound as it does not contribute to long-term network stability or learning. It also risks losing valuable diagnostic information that could prevent future incidents. A third incorrect approach is to focus solely on the application layer or end-user reports without investigating the underlying network infrastructure. While end-user experience is the ultimate measure of service availability, network issues often manifest at lower layers. Neglecting to examine the network path, routing, and device health means the root cause, which is likely network-related, will be missed. This is professionally deficient as it fails to address the core problem and leads to a reactive, rather than proactive, approach to network management. Professional reasoning. Professionals should employ a structured troubleshooting framework. This typically involves 1. Defining the problem clearly, including scope and impact. 2. Gathering information through monitoring tools, logs, and device status. 3. Formulating hypotheses based on the gathered information. 4. Testing hypotheses systematically, starting with the most probable and simplest causes. 5. Implementing solutions based on verified hypotheses. 6. Verifying the resolution and documenting the process and findings. This systematic approach ensures that troubleshooting is efficient, effective, and contributes to the overall stability and reliability of the enterprise network. Question 4. System analysis indicates that an enterprise network is experiencing intermittent connectivity issues affecting a critical business application. The network utilizes OSPF as its primary routing protocol. Initial investigation suggests that routing instability, characterized by frequent route changes and flapping, is the root cause. The network engineering team is under pressure to restore full application functionality immediately. Considering the principles of advanced routing and services as defined by the ENARSI exam objectives, What is the most professional and technically sound approach to address this OSPF instability? Option A. Propose a complete migration to a different routing protocol, such as IGP or BGP, to bypass the perceived issues with OSPF, without a thorough impact analysis. Option B. Implement a detailed OSPF troubleshooting methodology, focusing on identifying and rectifying the root cause of the instability, which may involve analyzing timers, neighbor relationships, network types, and area design, before considering any significant configuration changes. Option C. Immediately reconfigure OSPF timers to more aggressive values across the entire OSPF domain to expedite convergence and mask the underlying instability. Option D. Revert the OSPF configuration to a known stable state from several weeks prior, without investigating the specific events or configuration changes that may have led to the current instability. The correct answer is B. Implement a detailed OSPF troubleshooting methodology, focusing on identifying and rectifying the root cause of the instability, which may involve analyzing timers, neighbor relationships, network types, and area design, before considering any significant configuration changes. Explanation: scenario analysis. This scenario presents a common challenge in enterprise network design, where a critical service relies on a routing protocol's stability and predictability. The professional must balance the immediate need for service availability with the long-term implications of routing protocol configuration choices. The challenge lies in understanding the subtle but significant differences in how routing protocols handle network changes and converge, and how these differences can impact application performance and stability, especially in a large, complex enterprise environment. The pressure to restore service quickly can lead to hasty decisions that might not be optimal for the overall network health. Correct approach analysis. The correct approach involves a thorough understanding of the chosen routing protocol's convergence characteristics and its behavior under various failure scenarios. For OSPF, this means recognizing that its link-state nature allows for rapid and consistent convergence when configured correctly. By understanding the impact of timers, network types, and area design on convergence speed and stability, a network engineer can make informed decisions about how to best restore service. This approach prioritizes a stable and predictable routing environment, which is crucial for enterprise applications that are sensitive to routing changes. Adhering to Cisco's best practices for OSPF deployment, as outlined in the ENARSI curriculum, ensures that the chosen solution is robust and scalable. This aligns with professional responsibility to maintain network integrity and service availability through technically sound and well-reasoned configurations. Incorrect approaches analysis. One incorrect approach would be to hastily reconfigure the OSPF network with aggressive timer values without fully understanding the potential for routing instability. While this might seem like a quick fix, it can lead to flapping routes, increased CPU utilization on routers, and unpredictable application behavior, ultimately exacerbating the problem. This demonstrates a failure to apply sound engineering principles and a disregard for the potential negative consequences of rapid, unanalyzed changes. Another incorrect approach would be to consider migrating to a different routing protocol without a comprehensive analysis of the existing network's requirements and the implications of such a significant change. Such a decision, made under pressure, could introduce new complexities and potential issues, especially if the new protocol is not fully understood or if the existing infrastructure is not optimized for it. This represents a failure in systematic problem solving and a lack of due diligence. A third incorrect approach would be to simply revert to a previous, potentially outdated, configuration without investigating the root cause of the OSPF instability. While this might temporarily restore service, it fails to address the underlying issue, leaving the network vulnerable to future disruptions and demonstrating a lack of proactive problem solving. Professional reasoning. Professionals should employ a structured decision-making framework when faced with routing protocol instability. This framework includes 1. Thoroughly understanding the current network state and the observed behavior. 2. Analyzing the specific routing protocol's characteristics and how they relate to the observed issues. 3. Identifying potential configuration changes or troubleshooting steps based on best practices and the ENARSI curriculum. 4. Evaluating the potential impact of each proposed solution on network stability, application performance, and security. 5. Implementing the chosen solution methodically with clear rollback plans. 6. Monitoring the network closely after implementation to confirm resolution and identify any unintended consequences. This systematic approach ensures that decisions are data-driven, technically sound, and aligned with the goal of maintaining a robust and reliable enterprise network. Question 5. Regulatory review indicates that a proposed implementation of BGP route filtering to enhance network stability and security within a U.S.-based enterprise network may have unintended consequences on compliance with federal regulations governing telecommunications and data protection. Which of the following approaches best addresses this regulatory concern? Option A. Conduct a detailed impact assessment of the BGP route filtering implementation against relevant U.S. federal regulations, such as FCC rules and NIST guidelines, to identify and mitigate any potential compliance risks before deployment. Option B. Proceed with the BGP route filtering implementation based on performance improvement metrics, assuming that enhanced network stability will inherently satisfy regulatory requirements. Option C. Implement the BGP route filtering using the vendor's default configuration settings, as these are generally considered secure and compliant. Option D. Postpone the BGP route filtering implementation until a specific regulatory change mandates such a measure, to avoid unnecessary complexity. Correct answer is A. Conduct a detailed impact assessment of the BGP route filtering implementation against relevant U.S. federal regulations, such as FCC rules and NIST guidelines, to identify and mitigate any potential compliance risks before deployment. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent tension between implementing a new technology for improved network performance and ensuring compliance with established regulatory frameworks that govern data handling and network security. The challenge lies in proactively identifying potential compliance gaps before deployment, rather than reacting to them after an incident, which could lead to significant penalties, reputational damage, and service disruption. The need for deep analysis stems from the complexity of modern networking protocols and the evolving regulatory landscape. Correct approach analysis. The correct approach involves a thorough impact assessment that specifically evaluates the proposed BGP route filtering implementation against the relevant U.S. regulatory framework, such as the Federal Communications Commission, FCC, regulations concerning network reliability and data integrity, and potentially NIST guidelines for cybersecurity best practices. This assessment must identify how the filtering mechanism might affect the lawful interception of communications, the ability to maintain essential services during emergencies, and the protection of sensitive customer data from unauthorized access or manipulation. By proactively identifying and mitigating any potential conflicts with these regulations, the organization demonstrates due diligence and a commitment to lawful and secure network operations. This approach aligns with the ethical obligation to operate within legal boundaries and protect user data. Incorrect approaches analysis. Implementing the BGP route filtering without a specific regulatory impact assessment is a failure to adhere to due diligence principles. This approach risks violating regulations that mandate network stability and the integrity of data transmission. For instance, overly aggressive filtering could inadvertently block critical traffic necessary for emergency services or lawful government access, leading to regulatory penalties. Deploying the filtering based solely on performance metrics without considering regulatory implications is also a significant failure. While performance is important, it cannot supersede legal and ethical obligations. This approach could lead to unintended consequences that violate data privacy laws or network security standards, such as the Health Insurance Portability and Accountability Act, HIPAA, if protected health information is transmitted over the network. Relying on vendor default configurations for BGP route filtering without independent verification against U.S. regulations is another professionally unacceptable approach. Vendor defaults are designed for general use and may not account for specific industry or national regulatory requirements. This can lead to non-compliance, as the organization cannot claim ignorance of the law when a specific assessment was not performed. Professional reasoning. Professionals should adopt a proactive and risk-aware approach. The decision-making process should begin with identifying all applicable regulatory frameworks relevant to the technology being implemented. This is followed by a comprehensive impact assessment that maps the technical implementation to specific regulatory requirements. Any identified gaps or potential conflicts must be addressed through design modifications, policy updates, or documented risk acceptance with appropriate mitigation strategies. Continuous monitoring and periodic reassessment are crucial to ensure ongoing compliance as both technology and regulations evolve. Question 6. Benchmark analysis indicates a critical network segment supporting financial transaction processing has experienced a complete service outage. The urgency to restore operations is extremely high, as each minute of downtime incurs significant financial losses and potential regulatory scrutiny. Network engineers are on site, and initial observations suggest a potential routing instability issue. What is the most appropriate immediate course of action to ensure both rapid restoration and compliance with U.S. regulatory frameworks governing financial data integrity and availability? Option A. Proceed with aggressive configuration changes on the live network devices within the affected segment, based on the lead engineer's experience, to quickly re-establish routing paths. Option B. Rely on the lead engineer's extensive experience to manually reconfigure routing protocols on the live network devices, bypassing formal change control procedures due to the critical nature of the outage. Option C. Isolate the affected network segment and initiate a controlled diagnostic process using network monitoring tools to capture traffic and device states without making any configuration changes to the live environment, while simultaneously preparing a rollback plan for any subsequent remediation steps. Option D. Immediately reboot all network devices within the affected segment to clear any potential transient errors and restore connectivity as quickly as possible. The correct answer is C. Isolate the affected network segment and initiate a controlled diagnostic process using network monitoring tools to capture traffic and device states without making any configuration changes to the live environment, while simultaneously preparing a rollback plan for any subsequent remediation steps. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise networking, where a critical service outage necessitates rapid troubleshooting and remediation. The professional challenge lies in balancing the urgency of restoring service with the need to adhere to established operational procedures and regulatory compliance, particularly concerning data integrity and security. The pressure to resolve the issue quickly can lead to shortcuts that might compromise these critical aspects. Correct approach analysis. The correct approach involves a systematic, documented process that prioritizes data preservation and compliance. This aligns with best practices in IT service management, and in a regulated environment like the U.S. financial sector, would be mandated by frameworks such as NIST, National Institute of Standards and Technology, guidelines, particularly those related to incident response and business continuity. Specifically, NIST SB 800-61 Rev. 2 Computer Security Incident Handling Guide emphasizes the importance of preserving evidence and documenting all actions taken during an incident. This ensures that the root cause can be accurately identified, future occurrences can be prevented, and any potential audit or forensic requirements are met. By isolating the affected segment and performing diagnostics without altering the live environment, the integrity of the network and its data is maintained, fulfilling regulatory obligations to protect sensitive information and ensure service availability. Incorrect approaches analysis. One incorrect approach involves immediately rebooting all network devices in the affected segment without prior analysis. This is a regulatory failure because it bypasses the mandated incident response procedures that require evidence preservation. In the U.S., regulations like Sarbanes-Oxley (SOX) and HIPAA, Health Insurance Portability and Accountability Act, depending on the industry, require auditable logs and evidence of system behavior. A reboot can erase volatile memory containing crucial diagnostic information, making it impossible to determine the root cause or satisfy audit requirements. This action also risks exacerbating the problem or causing further data corruption, violating principles of data integrity and availability. Another incorrect approach is to proceed with configuration changes on the live network to attempt a quick fix without a rollback plan or proper change control. This is a significant ethical and regulatory failure. In regulated industries, unauthorized or undocumented changes can lead to noncompliance with security standards and operational procedures. For instance, PCI DSS, Payment Card Security Data Industry, Compliance requires strict change control processes for systems handling cardholder data. Such changes can introduce new vulnerabilities, disrupt other services, and make it impossible to revert to a known good state, leading to prolonged downtime and potential data breaches. A third incorrect approach involves relying solely on anecdotal evidence or the experience of a single engineer without consulting official documentation or established troubleshooting guides. While experience is valuable, it is not a substitute for a structured, evidence-based approach. This can lead to misdiagnosis and ineffective solution, prolonging the outage. From a regulatory standpoint, this approach fails to demonstrate due diligence and adherence to standardized operating procedures, which are often a requirement for compliance in critical infrastructure or sensitive data environments. It also undermines the principle of shared knowledge and best practices within an organization. Professional reasoning. Professionals should adopt a structured incident response framework. This involves 1. Identification and initial assessment of the incident. 2. Containment of the incident to prevent further damage. 3. Eradication of the root cause. 4. Recovery of affected systems. 5. Post-incident review and lessons learned. Throughout this process, meticulous documentation and adherence to change control policies are paramount. In a U.S. context, this aligns with NIST guidelines and industry-specific regulations. When faced with an outage, the decision-making process should prioritize preserving evidence, minimizing further impact, and following documented procedures, even under pressure. This ensures accountability, facilitates root cause analysis, and maintains compliance. Question 7. The efficiency study reveals that a critical customer-facing application is experiencing intermittent connectivity issues, leading to significant user complaints and potential revenue loss. Initial reports suggest that the application's ability to reach its backend database servers is intermittently failing. The network infrastructure includes multiple Cisco routers configured with BGP for external connectivity and OSP for internal routing. The application servers are located in a DMZ segment, and the database servers are in a secure internal segment. Which of the following approaches is the most effective for diagnosing and resolving this intermittent connectivity issue? Option A. Initiate a full network packet capture on the application servers and the database servers simultaneously, without first verifying basic network reachability. Option B. Immediately revert the firewall configuration in the DMZ to a previous known good state, assuming the issue is related to recent security policy changes. Option C. Analyze BGP peering status and BGP table entries on edge routers, and examine OSPF neighbor adjacencies and LSDB on internal routers to identify any routing anomalies or path changes affecting reachability to the database servers. Option D. Focus troubleshooting efforts exclusively on the application servers, checking their network interface configurations and application-level logs for errors. The correct answer is C. Analyze BGP peering status and BGP table entries on edge routers, and examine OSPF neighbor adjacencies and LSDB on internal routers to identify any routing anomalies or path changes affecting reachability to the database servers. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise network management, where a critical service outage impacts business operations. The professional challenge lies in rapidly identifying the root cause and implementing a solution while adhering to established operational procedures and minimizing further disruption. The urgency of the situation can lead to pressure to bypass standard protocols, which could have significant regulatory and operational consequences. Careful judgment is required to balance speed with thoroughness and compliance. Correct approach analysis. The correct approach involves a systematic troubleshooting methodology that prioritizes understanding the impact and then isolating the issue within the defined scope of the ENARSI. Exams focus on advanced routing and services. This includes leveraging diagnostic tools to analyze routing adjacencies, traffic flow patterns, and configuration states on affected devices. The emphasis on verifying the BGP peering status and examining the BGP table for route propagation issues directly addresses common failure points in enterprise routing. This methodical approach ensures that the resolution is accurate, prevents recurrence, and aligns with best practices for network stability and service availability, which are implicitly governed by service-level agreements, SLAs, and operational standards that fall under the purview of IT governance frameworks. Incorrect approaches analysis. One incorrect approach involves immediately reverting to a previous known good configuration without a thorough diagnostic analysis. This is professionally unacceptable because it fails to identify the root cause, potentially masking an underlying configuration drift or a more complex issue that could re-emerge. It also violates the principle of change management, which requires understanding the impact of any rollback. Another incorrect approach is to focus solely on the edge routing devices without considering the internal network path or service dependencies. This is a failure to conduct a comprehensive impact assessment, as the issue might stem from an intermediate device or a service failure that is indirectly affecting routing. Such an approach risks misdiagnosis and wasted effort. A third incorrect approach is to immediately escalate to a vendor support team without performing initial troubleshooting steps. While vendor support is crucial, a lack of preliminary diagnosis can lead to inefficient ticket management, increased resolution time, and potentially unnecessary charges if the issue is within the organization's control and expertise. This demonstrates a failure in professional due diligence and resource management. Professional reasoning. Professionals should adopt a structured troubleshooting framework. This begins with clearly defining the problem and its impact. Next, gather relevant data using diagnostic tools, focusing on the specific technologies covered by the ENARSI exam, such as BGP, OSP, IGAP, and MPLS. Analyze this data to form hypotheses about the root cause. Test these hypotheses systematically, prioritizing changes that have the least impact on other services. Document all findings and actions taken. If the issue persists, then escalate with comprehensive diagnostic information. This process ensures efficient problem resolution, minimizes risk, and maintains operational integrity. Question 8. Implementation of a new enterprise-wide routing policy requires careful consideration of routing protocol timer adjustments to ensure rapid convergence without compromising network stability. Which approach best balances these competing requirements while adhering to professional network engineering standards? Option A. Modify routing protocol timers based on recommendations from online forums without validating their applicability to the specific enterprise network. Option B. Systematically adjust routing protocol timers incrementally, starting with minor changes, and rigorously test the impact on network stability and convergence at each stage before proceeding. Option C. Make significant, broad changes to routing protocol timers based on general best practices without specific testing for the enterprise environment. Option D. Immediately reduce all routing protocol timers across the entire enterprise network to achieve the fastest possible convergence. The correct answer is B. Systematically adjust routing protocol timers incrementally, starting with minor changes, and rigorously test the impact on network stability and convergence at each stage before proceeding. Explanation. Scenario analysis. This scenario presents a professional challenge in network design, where a critical service relies on the stability and predictability of routing protocols. The challenge lies in balancing the need for rapid convergence during network changes with the potential for instability introduced by overly aggressive tuning. Misjudging the impact of routing protocol timers can lead to intermittent connectivity, service degradation, or even complete outages, directly affecting business operations and user experience. The professional must consider the specific characteristics of the enterprise network, including its size, topology, and the criticality of the services it supports, to make informed decisions about routing protocol behavior. Correct approach analysis. The correct approach involves a phased and controlled adjustment of routing protocol timers, starting with minor modifications and thoroughly testing the impact at each stage. This aligns with best practices for network change management, which emphasize minimizing risk and ensuring service continuity. By incrementally tuning timers and monitoring network behavior, engineers can identify thresholds where stability is compromised before a full-scale outage occurs. This methodical approach allows for a data-driven decision-making process, ensuring that changes are validated and that the network remains resilient. The focus is on achieving optimal convergence without sacrificing stability, a core principle in enterprise network engineering. Correct approach is analysis. Aggressively reducing all routing protocol timers across the entire enterprise network without prior testing or a clear understanding of the interdependencies between different routing domains is a significant regulatory and ethical failure. Such an approach disregards the principle of due diligence in network design and implementation. It creates an unacceptable risk of widespread network instability, potentially violating service-level agreements, SLAs, with internal or external stakeholders. This reckless modification can lead to data loss or service unavailability, which could have financial and reputational consequences. Furthermore, it demonstrates a lack of professional responsibility by prioritizing speed over stability and thoroughness, failing to uphold the standards of competent network engineering. Making broad, sweeping changes to routing protocol timers based on anecdotal evidence or a desire for immediate convergence, without a comprehensive impact assessment, is also professionally unacceptable. This approach ignores the potential for unforeseen interactions between different routing protocols or network segments. It can lead to routing loops, black holes, or excessive CPU utilization on network devices, all of which contribute to network instability. This demonstrates a failure to apply a systematic and analytical approach to network management, potentially leading to service disruptions that could be deemed negligent. Implementing changes to routing protocol timers without establishing baseline metrics and monitoring tools to track convergence times and network stability is another critical failure. Without a baseline, it is impossible to objectively determine if the changes have had the desired effect or if they have introduced new problems. This lack of measurement and validation means that the network's performance is being managed reactively rather than proactively, increasing the likelihood of prolonged outages when issues arise. This approach falls short of professional standards that require verifiable results and continuous improvement. Professional reasoning. Professionals should adopt a structured approach to network changes, particularly those affecting routing protocols. This involves 1. Thoroughly understanding the existing network topology, traffic patterns, and service criticality. 2. Defining clear objectives for the change, such as improving convergence time for specific scenarios. 3. Developing a detailed change plan that includes rollback procedures and a testing methodology. 4. Implementing changes in a controlled environment or during scheduled maintenance windows. 5. Closely monitoring network performance and stability using appropriate tools before, during, and after the change. 6. Documenting all changes and their observed impacts. This systematic process ensures that network stability is maintained while achieving desired performance improvements, adhering to professional ethics and best practices. Question 9. Market research demonstrates a growing demand for real-time data analytics and low-latency application performance within enterprise networks. To meet this demand, a network engineering team is proposing the implementation of advanced routing protocols and dynamic service insertion across multiple data centers. Before proceeding with the implementation, what is the most critical step to ensure compliance with U.S. regulatory frameworks governing data handling and network security? Option A. Conduct a comprehensive impact assessment that includes a thorough review of relevant U.S. data privacy and security regulations, engagement with legal and compliance departments, and the development of mitigation strategies for identified risks. Option B. Rely solely on vendor documentation for security best practices, assuming that the advanced routing protocols and services are inherently compliant with all U.S. regulations. Option C. Prioritize the rapid deployment of the new routing protocols and services to gain a competitive advantage, assuming existing security measures will adequately protect data. Option D. Implement the proposed changes immediately and address any potential regulatory concerns that may arise post-deployment through reactive adjustments. The correct answer is A. Conduct a comprehensive impact assessment that includes a thorough review of relevant U.S. data privacy and security regulations, engagement with legal and compliance departments, and the development of mitigation strategies for identified risks. Explanation. This scenario presents a professional challenge due to the inherent tension between implementing advanced network services for business agility and adhering to the strict regulatory framework governing data handling and network security within the United States. The ENARSI exam focuses on implementing enterprise advanced routing and services, implying a need for robust, scalable, and secure network solutions. The challenge lies in ensuring that any network design or modification, particularly those involving advanced routing protocols and services, does not inadvertently create vulnerabilities or noncompliance with U.S. regulations such as HIPAA, Health Insurance Portability and Accountability Act. if patient data is involved, or general data privacy laws. The need for deep analysis of impact assessment is paramount to avoid costly remediation, reputational damage, and legal repercussions. The correct approach represents best professional practice because it prioritizes a thorough, proactive assessment of the potential impact of network changes on regulatory compliance and security posture. This involves engaging relevant stakeholders, including legal and compliance teams, to understand the specific requirements of applicable U.S. laws. By conducting a comprehensive risk assessment and developing mitigation strategies before implementation, network engineers demonstrate due diligence and a commitment to responsible technology deployment. This aligns with the ethical obligation to protect sensitive data and ensure the integrity of network services, as implicitly expected within the U.S. regulatory environment for enterprise networks. An incorrect approach that bypasses or inadequately assesses regulatory implications is professionally unacceptable. For instance, prioritizing speed of deployment over a thorough impact assessment without consulting compliance experts could lead to violations of data privacy laws. This failure to consider the regulatory landscape is an ethical lapse, as it risks exposing the organization to penalties for non-compliance. Another incorrect approach might be to assume existing security measures are sufficient without verifying their applicability to the new services or protocols being implemented. This demonstrates a lack of professional rigor and an abdication of responsibility to ensure the network meets all legal and security mandates. Such oversights can result in significant fines, loss of customer trust, and potential legal action, all of which are direct consequences of failing to perform a proper impact assessment within the U.S. regulatory context. The professional decision-making process for similar situations should involve a structured approach. 1. Identify all applicable U.S. regulations relevant to the network services being implemented, e.g., data privacy security standards. 2. Engage with legal, compliance, and security teams early in the design phase. 3. Conduct a detailed risk assessment, identifying potential compliance gaps and security vulnerabilities introduced by the proposed changes. 4. Develop and document mitigation strategies and contingency plans. 5. Obtain formal approval from all relevant stakeholders before proceeding with implementation. 6. Establish ongoing monitoring and auditing processes to ensure continued compliance. Question 10. Market research demonstrates a growing demand for faster service provisioning within enterprise networks, prompting a business unit to request the immediate implementation of a new dynamic routing protocol to support a critical application rollout. The network engineering team is under pressure to deploy this change within a tight deadline. What is the most professional and responsible approach to ensure network stability and compliance while meeting the business need? Option A. Proceed with the implementation using vendor default configurations for the new routing protocol, assuming it will integrate seamlessly with the existing network. Option B. Implement the new routing protocol on a small subset of network devices and monitor performance, making adjustments as issues arise without a predefined rollback strategy. Option C. Prioritize the business unit's deadline by implementing the routing protocol immediately and address any network issues that may arise post-deployment. Option D. Conduct a thorough impact assessment, including traffic analysis, compatibility checks with existing infrastructure, security implications, and develop a detailed rollback plan before proceeding with the implementation. The correct answer is D. Conduct a thorough impact assessment, including traffic analysis, compatibility checks with existing infrastructure, security implications, and develop a detailed rollback plan before proceeding with the implementation. Explanation. This scenario presents a professional challenge due to the inherent conflict between rapid network deployment and the need for thorough impact assessment, especially in a regulated environment like enterprise networking. The ENARSI exam focuses on advanced routing and services, implying a context where network stability, security, and performance are critical. Misjudging the impact of a new routing protocol implementation can lead to significant service disruptions, financial losses, and reputational damage. The challenge lies in balancing the urgency of business needs with the meticulous planning and validation required to mitigate risks. The correct approach represents best professional practice because it prioritizes a systematic and documented process for evaluating changes. This aligns with industry best practices for network change management, which are often implicitly or explicitly tied to regulatory compliance frameworks that mandate risk assessment and mitigation for critical infrastructure. By performing a comprehensive impact assessment, including traffic analysis, compatibility checks, and rollback planning, network engineers ensure that the proposed changes are understood, validated, and that contingency plans are in place. This proactive stance minimizes the likelihood of unforeseen negative consequences and demonstrates due diligence in maintaining network integrity and service availability, which are often subject to service-level agreements, SLAs, and potentially regulatory oversight depending on the industry. An incorrect approach that bypasses or inadequately performs impact assessment demonstrates a failure to adhere to professional standards of care. Specifically, implementing a new routing protocol without understanding its potential effects on existing traffic flows, security policies, or device compatibility is a direct violation of responsible network engineering principles. This could lead to network instability, security vulnerabilities, e.g., unintended routing loops, denial of service conditions, and noncompliance with internal policies or external regulations that require a stable and secure network. Such actions expose the organization to significant operational risks and potential legal or financial repercussions if service disruptions occur. Another incorrect approach might involve relying solely on vendor default configurations without assessing their suitability for the specific enterprise environment. This overlooks the unique requirements and existing infrastructure, increasing the risk of misconfiguration and subsequent network issues, which again would be a failure in professional due diligence. The professional decision-making process for similar situations should involve a structured change management framework. This framework typically includes 1. Request for change, RFC submission detailing the proposed change. 2. Impact assessment, which is the core of this question, evaluating potential effects on all relevant network aspects. 3. Planning and design, including detailed configuration steps and rollback procedures. 4. Testing and validation, often in a lab environment or during a maintenance window. 5. Implementation. 6. Post-implementation verification and monitoring. Professionals must always advocate for and adhere to this structured process, even under pressure for rapid deployment, as the long-term consequences of skipping critical assessment phases far outweigh any short-term gains. Question 11. Operational review demonstrates that a recent BGP configuration change, intended to optimize route selection, has led to significant latency and packet loss for critical business applications. The network team is under pressure to restore application performance immediately. What is the most appropriate immediate course of action? Option A. Implement additional CoS policies across the network to prioritize traffic for the affected applications, assuming the BGP change is not the sole cause. Option B. Initiate a phased rollback of the BGP configuration change to the previous stable state, followed by controlled testing to identify the specific problematic configuration element. Option C. Focus on troubleshooting the application servers and their direct network connections, as the routing change is unlikely to be the primary driver of application-level performance degradation. Option D. Proceed with further network optimizations and upgrades, as the BGP change may have uncovered underlying network capacity issues that need addressing. The correct answer is B. Initiate a phased rollback of the BGP configuration change to the previous stable state, followed by controlled testing to identify the specific problematic configuration element. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise network management where a critical routing protocol update intended to improve network efficiency has an unforeseen negative impact on application performance. The challenge lies in balancing the need for network optimization with the absolute requirement of maintaining application availability and user experience. The pressure to quickly resolve the issue, coupled with the potential for widespread business disruption, necessitates a methodical and well-justified approach. The complexity arises from the interconnectedness of routing, services, and application behavior, making it difficult to isolate the root cause without a systematic impact assessment. Correct approach analysis. The correct approach involves a phased rollback and verification strategy. This represents best professional practice because it prioritizes minimizing further disruption. By rolling back the change to a known stable state, the immediate impact on application performance is eliminated, allowing for a return to normal operations. Subsequent, controlled testing in a lab environment or during a maintenance window with detailed monitoring allows for the identification of the specific configuration or protocol behavior that caused the issue. This methodical approach aligns with ITIL principles of incident management and change management, emphasizing service restoration and preventing recurrence. From a regulatory perspective, while the ENARSI exam doesn't focus on specific external regulations, the implicit expectation in enterprise environments is to maintain service continuity and adhere to internal service level agreements, SLAs, which this approach directly supports. Incorrect approaches analysis. Implementing a broad network-wide configuration change without a rollback plan is a significant regulatory and ethical failure. It demonstrates a disregard for service continuity and potential business impact, violating implicit SLAs and potentially internal governance policies. This approach prioritizes the perceived benefit of the update over the risk of failure, which is unprofessional and can lead to severe business disruption and financial losses. Attempting to fix the application issue without addressing the underlying routing change is also professionally unacceptable. This is akin to treating symptoms rather than the cause. It prolongs the incident, wastes resources, and fails to prevent the issue from recurring. It also indicates a lack of understanding of network interdependencies, a core competency for ENARSI. Ethically, it fails to provide a complete and lasting solution. Ignoring the reported application performance issues and continuing with further network optimizations is a severe failure. This demonstrates a complete disregard for user experience and business operation. It is a direct violation of the responsibility to maintain a functional and reliable network. Such an approach would likely lead to significant business impact, customer dissatisfaction, and potential breaches of service agreements. Professional reasoning. Professionals facing such a situation should employ a structured incident response and change management framework. The immediate priority is service restoration. This involves reverting to a known good state. Once service is restored, a thorough root cause analysis (RCA) must be performed. This RCA should involve detailed log analysis, packet captures, and simulation if possible. The change that caused the issue should be meticulously reviewed, and the impact assessment process for future changes must be strengthened to include more rigorous testing and validation steps, potentially involving application owners and end-user representatives. Question 12. Investigation of a critical enterprise application experiencing intermittent connectivity issues traced back to instability within the OSP2 routing domain. The application's performance is highly sensitive to routing convergence times and the accuracy of routing information. The network administrator suspects that the OSP2 configuration might be vulnerable to external manipulation or internal misconfigurations that could lead to suboptimal routing paths or route flapping. What is the most effective approach to enhance the stability and security of the OSP2 routing protocol in this environment? Option A. Configure all OSP2 interfaces as passive, preventing any OSP2 neighbor adjacencies from forming on these interfaces. Option B. Implement OSP2 authentication but do not implement any route filtering or summarization, relying on the authentication to prevent all routing issues. Option C. Implement OSP2 authentication and utilize prefix lists to filter incoming and outgoing routing updates, along with route summarization on distribution layer interfaces. Option D. Disable OSP2 authentication on all interfaces to reduce overhead and simplify configuration. The correct answer is C. Implement OSP2 authentication and utilize prefix lists to filter incoming and outgoing routing updates, along with route summarization on distribution layer interfaces. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise network design, where a critical service relies on a routing protocol that is susceptible to instability under certain conditions. The challenge lies in ensuring the resilience and availability of this service, while adhering to best practices for routing protocol configuration and security. The need to balance performance, stability, and security in a complex routing environment requires careful consideration of protocol behavior and potential attack vectors. The professional challenge is to implement a robust solution that mitigates risks without introducing unnecessary complexity or compromising network functionality. Correct approach analysis. The correct approach involves implementing route filtering and authentication mechanisms specifically designed to enhance the stability and security of the OSP2 routing protocol. Route filtering, using prefix lists and distribute lists, prevents the propagation of potentially malicious or incorrect routing information, thereby enhancing network stability. OSP2 authentication, e.g., MD5 or SHA-256, ensures that only legitimate routers can exchange routing updates, preventing unauthorized routers from injecting false routes or disrupting the routing process. This combination directly addresses the vulnerabilities of OSP2 by controlling what information is accepted and ensuring the integrity of the information exchanged. This aligns with Cisco's recommended best practices for securing and stabilizing OSP deployments in enterprise networks, which are implicitly expected to be followed in the context of the ENARSI exam. Incorrect approaches analysis. Disabling OSP2 authentication entirely is a significant security failure. It leaves the routing protocol vulnerable to spoofing attacks, where an attacker could inject false routing information, leading to traffic blackholing or redirection, and ultimately service disruption. This is a direct violation of fundamental network security principles. Implementing OSP2 authentication, but failing to implement any form of route filtering or summarization creates a different kind of vulnerability. While authentication protects against rogue routers, it does not prevent the propagation of incorrect or suboptimal routes from legitimate but misconfigured routers. This can lead to routing instability and suboptimal traffic paths, impacting service availability. Relying solely on passive interfaces for OSP2 neighbors without authentication or filtering offers minimal security and stability benefits. Passive interfaces prevent OSP hellos and updates from being sent out on those interfaces, which is useful for preventing routing on non-routing interfaces. However, it does not prevent the router from accepting OSP updates if they are received, nor does it authenticate the source of those updates. This approach does not address the core vulnerabilities of OSP2 in this scenario. Professional reasoning. Professionals facing such a scenario should first conduct a thorough risk assessment of the critical service and its reliance on OSP2. They should then consult Cisco's official documentation and best practices for OSP2 security and stability. The decision-making process should prioritize a layered security approach, combining authentication to verify the identity of neighbors with filtering to control the routing information exchanged. This ensures both the integrity of the routing domain and the accuracy of the routing information. When evaluating solutions, consider the impact on network performance and operational complexity. Always aim for the most secure and stable configuration that meets the functional requirements of the network. Question 13. What factors determine the most effective security posture for BGP peering within a Cisco enterprise network, considering the potential for route hijacking and the need for network stability? Option A. The implementation of BGP authentication and prefix filtering to validate peer identity and accepted routes. Option B. The exclusive use of static routing for all critical network paths to eliminate dynamic routing vulnerabilities. Option C. The sole reliance on BGP route dampening to mitigate route flapping without addressing underlying causes. Option D. The assumption of inherent trust among all BGP peers due to established network relationships. Correct answer is A. The implementation of BGP authentication and prefix filtering to validate peer identity and accepted routes. Explanation. This scenario presents a common challenge in enterprise networking, ensuring the integrity and availability of critical routing information across a distributed network. The professional challenge lies in balancing the need for rapid convergence and efficient routing updates with the potential for misconfigurations or malicious injection of routing data that could disrupt services. Careful judgment is required to select and implement appropriate security mechanisms without introducing undue complexity or performance degradation. The correct approach, focusing on BGP security features like prefix filtering and authentication, represents best professional practice because it directly addresses the vulnerabilities inherent in BGP. Prefix filtering, implemented through access control lists, ACL or route maps, ensures that only legitimate prefixes are accepted from peers, preventing the advertisement of unauthorized or malformed routes. BGP authentication, e.g., MD5 or TCP-AL, verifies the identity of BGP peers, preventing unauthorized routers from establishing peering sessions and injecting false routing information. These measures align with general cybersecurity principles of least privilege and defense in depth, aiming to protect the routing infrastructure from both accidental and intentional disruptions. An incorrect approach that relies solely on static routing for critical paths would fail because it negates the dynamic nature of BGP, which is essential for scalability and resilience in enterprise networks. While static routes are predictable, they lack the automatic adaptation to network changes that BGP provides, leading to potential outages if link failures occur. Furthermore, managing static routes across a large enterprise would be operationally burdensome and error-prone. Another incorrect approach, neglecting any form of BGP security and assuming all peers are trusted, is professionally unacceptable due to a fundamental failure to acknowledge and mitigate known security risks. BGP is a widely targeted protocol, and assuming implicit trust opens the network to significant threats, including route hijacking and denial-of-service attacks. This approach violates the principle of assuming a hostile network environment and fails to implement basic security controls. A third incorrect approach, implementing route dampening without addressing the root cause of instability, is also flawed. Route dampening is a mechanism to suppress flapping routes, but it does not prevent the initial instability or the injection of incorrect routes. It is a reactive measure, not a proactive security control, and can inadvertently mask legitimate route changes, leading to suboptimal routing or connectivity issues. The professional reasoning process for similar situations should involve a thorough risk assessment of the routing protocol's attack surface, followed by the implementation of layered security controls. This includes understanding the specific vulnerabilities of the protocol in use, BGP in this case, identifying potential threat vectors, and selecting appropriate mitigation strategies. Prioritizing proactive security measures over reactive ones, and ensuring that security controls are integrated into the network design from the outset, are key to building a robust and secure enterprise routing infrastructure. Question 14. When evaluating the optimal BGP path selection for an enterprise network with multiple redundant WAN links, which configuration strategy best ensures predictable and stable inbound and outbound traffic flow, considering the order of BGP path selection attributes? Option A. Implement as path prepending on all outbound paths to artificially lengthen the as path and make them appear less desirable. Option B. Configure a lower MED, multi-exit discriminator, value on the preferred inbound path to encourage its selection by external BGP peers. Option C. Rely solely on the default BGP path selection algorithm, assuming it will automatically choose the most optimal paths based on network topology. Option D. Configure a higher local preference on the preferred outbound path, and utilize as path prepending on the inbound path of the less preferred WAN link to influence inbound traffic. The correct answer is D. Configure a higher local preference on the preferred outbound path, and utilize as path prepending on the inbound path of the less preferred WAN link to influence inbound traffic. Explanation. This scenario presents a common challenge in enterprise network design, ensuring robust and resilient routing in the face of potential failures, specifically focusing on the implementation of BGP path selection attributes. A professional challenge lies in understanding the intricate interplay of these attributes and how they influence traffic flow, especially when multiple paths exist. A deep understanding of BGP's decision process is crucial for making informed design choices that align with business objectives for availability and performance, without introducing unintended consequences or security vulnerabilities. The regulatory framework for this exam, the 300-410 ENARSI, implicitly guides best practices by emphasizing efficient, secure, and reliable network operations. While no explicit laws govern BGP attribute selection in a direct sense, adherence to industry best practices, as embodied by Cisco's recommended configurations and the principles of network engineering, is paramount. The correct approach leverages a thorough understanding of BGP path selection attributes and their order of precedence. By prioritizing attributes that directly influence path desirability and stability, such as local preference for outbound traffic control and as path for inbound traffic influence, the network engineer can engineer specific traffic flows. This methodical application of BGP attributes ensures that the most optimal paths are chosen based on defined criteria, leading to predictable and resilient routing. This aligns with the professional responsibility to design networks that are not only functional but also efficient and maintainable, minimizing downtime and maximizing resource utilization. An incorrect approach might involve solely relying on default BGP behavior without explicit configuration. This can lead to unpredictable path selection, especially in complex topologies with multiple BGP peers and diverse path options. Such a failure to actively manage BGP path selection can result in suboptimal routing, increased latency, or even network instability if a less desirable path is chosen during a failure event. Another incorrect approach could be misapplying BGP attributes. For instance, using as path prepending to influence inbound traffic when local preference would be the more appropriate and effective tool for outbound traffic shaping. This demonstrates a lack of understanding of how each attribute impacts the BGP decision process and can lead to unintended routing loops or traffic black holes. A further incorrect approach might be to configure attributes without considering their global or local scope, leading to inconsistent path selection across different routers in the network, thereby undermining the overall routing stability and predictability. The professional decision-making process should involve a systematic evaluation of business requirements for traffic flow and resilience. This includes understanding the desired inbound and outbound traffic engineering goals. Subsequently, the engineer must possess a deep knowledge of BGP's path selection algorithm and the specific attributes available to influence it. The process should involve designing a BGP configuration that explicitly manipulates these attributes in the correct order of precedence to achieve the desired outcomes. Testing and validation of the implemented configuration are critical steps to ensure that the intended path selection is occurring and that no adverse effects are introduced. Question 15. Quality control measures reveal that a newly deployed BGP peering session with a trusted external partner is exhibiting unexpected route advertisements, potentially impacting internal network stability and security. The network administrator needs to implement a solution to ensure that only legitimate and expected routes are exchanged, preventing the propagation of unauthorized or incorrect routing information. The primary goal is to enhance the security posture of the BGP peering without disrupting legitimate traffic flow. Which of the following BGP configuration strategies best addresses this requirement while adhering to enterprise routing security best practices as outlined in the ENARSI curriculum? Option A. Disable all inbound route filtering on the BGP peering session to maximize route learning and ensure the most optimal path selection, relying solely on the partner's network integrity. Option B. Implement prefix lists to define the specific IP address ranges that are permitted to be advertised and accepted, and use route maps to apply these prefix lists to the BGP neighbor, controlling both inbound and outbound route propagation. Option C. Configure BGP neighbor authentication using MD5 passwords to verify the identity of the BGP peer, and accept all advertised routes as long as the peer is authenticated. Option D. Utilize as path access lists to filter routes based on the autonomous system path, allowing only routes originating from the trusted partners as number. The correct answer is B. Implement prefix lists to define the specific IP address ranges that are permitted to be advertised and accepted, and use route maps to apply these prefix lists to the BGP neighbor, controlling both inbound and outbound route propagation. Explanation. The scenario presents a common challenge in enterprise network design, ensuring secure and efficient routing of sensitive traffic while adhering to established security policies and best practices. The professional challenge lies in balancing the need for network performance and accessibility with the imperative to protect data from unauthorized access or modification. This requires a deep understanding of routing protocols, security features, and their interplay within a Cisco enterprise environment, specifically as covered by the ENARSI exam. The correct approach represents best professional practice because it directly addresses the security requirements by implementing a robust and granular access control mechanism at the network edge. Using prefix lists and route maps to filter BGP updates ensures that only authorized and expected routes are advertised and accepted, thereby preventing the propagation of potentially malicious or incorrect routing information. This aligns with the principle of least privilege and defense in depth, fundamental to secure network operations. The ENARSI curriculum emphasizes the configuration and verification of these features for secure routing, An incorrect approach that involves accepting all BGP routes without any filtering is professionally unacceptable due to significant security and stability risks. This would violate the principle of validating incoming routing information, potentially allowing an attacker to inject false routes, route injection, or overwhelm the network with unnecessary routing updates, leading to instability and denial of service. This directly contravenes the security objectives of a well-designed enterprise network and the best practices taught in ENARSI. Another incorrect approach that relies solely on as-path filtering without prefix lists or route maps is also professionally deficient. While as-path filtering can prevent certain types of attacks, it is not granular enough to control the specific IP prefixes being advertised. This could still allow for the advertisement of unwanted or malicious prefixes originating from a trusted as, leading to suboptimal routing or security breaches. It fails to provide the necessary control over the actual routing information exchanged. A further incorrect approach that involves disabling BGP authentication is a critical security failure. BGP authentication, e.g., using MD5 passwords, is a fundamental mechanism to verify the identity of BGP peers and prevent unauthorized routers from participating in the routing process. Disabling it exposes the network to man-in-the-middle attacks and unauthorized route injection, directly contradicting the security principles emphasized in enterprise routing and covered in ENARSI. The professional decision-making process for similar situations should involve a thorough risk assessment, a clear understanding of the network's security policy, and the application of appropriate technical controls. This includes 1. Identifying critical assets and traffic flows. 2. Defining acceptable routing policies and expected routes. 3. Selecting and configuring routing protocols and security features that enforce these policies. 4. Implementing granular filtering and authentication mechanisms. 5. Regularly reviewing and auditing routing configurations and security logs. 6. Staying updated on emerging threats and vulnerabilities related to routing protocols. This systematic approach ensures that the network is not only functional but also secure and resilient. Question 16. The risk matrix shows a moderate likelihood of unauthorized access to sensitive financial data due to potential route manipulation within the enterprise network. The IT security team has flagged the current OSPF implementation as a contributing factor, citing the broad advertisement of internal routing information. The network engineering team is tasked with reconfiguring the OSPF deployment to mitigate this risk without significantly impacting legitimate interdepartmental communication or introducing new operational overhead. Which of the following OSPF configuration strategies best addresses the identified risk while adhering to enterprise security best practices? Option A. Configure all internal interfaces as passive and only enable OSPF on the WAN edge routers to advertise external routes. Option B. Enable OSPF on all interfaces, including those connecting to end-user workstations, and rely on host-based firewalls for security. Option C. Remove OSPF entirely and implement static routing for all internal network segments to reduce complexity. Option D. Implement OSPF authentication between all adjacent routers and configure route summarization on distribution layer routers to advertise only aggregated internal network prefixes to the core. The correct answer is D. Implement OSPF authentication between all adjacent routers and configure route summarization on distribution layer routers to advertise only aggregated internal network prefixes to the core. Explanation. This scenario presents a common challenge in enterprise network design, balancing the need for efficient routing with the potential for security vulnerabilities and operational complexity. The core issue revolves around the implementation of a routing protocol that, while offering advanced features, can inadvertently expose sensitive internal network segments if not properly secured and managed. The professional challenge lies in selecting and configuring the routing solution in a way that adheres to best practices for network security and stability, while also meeting performance requirements. Careful judgment is required to avoid introducing new risks or compromising existing security postures. The correct approach represents best professional practice because it prioritizes a layered security model and adheres to the principle of least privilege. By segmenting the network and implementing access control lists, ACL, at the appropriate boundaries, it ensures that routing information is exchanged only between trusted entities and that sensitive internal routes are not advertised unnecessarily. This aligns with general cybersecurity principles and the implicit requirements of maintaining a secure and stable enterprise network, which are foundational to responsible IT operations. The focus on explicit control and verification of routing advertisements is a hallmark of robust network engineering. An incorrect approach that involves enabling OSPF on all interfaces without proper authentication or summarization would be professionally unacceptable. This failure would violate the principle of least privilege by exposing routing information to potentially untrusted segments and increasing the attack surface. It could lead to route injection attacks or denial of service conditions if an attacker can manipulate routing updates. Another incorrect approach, such as relying solely on passive interfaces for all internal segments without considering the need for intersegment routing, would lead to network segmentation that is too rigid and prevents necessary communication, impacting business operations. Finally, an approach that prioritizes speed of deployment over security by skipping ACL configuration would be a direct abdication of responsibility for network security, creating a significant vulnerability. Professionals should employ a decision-making framework that begins with a thorough understanding of business requirements and security policies. This involves assessing the network topology, identifying critical assets and sensitive data, and understanding the threat landscape. The next step is to evaluate routing protocol options based on their security features, scalability, and operational complexity. Configuration should then follow a principle of defense in depth, with security controls implemented at multiple layers. Regular auditing and monitoring of routing configurations and traffic patterns are essential to detect and mitigate potential issues proactively. Question 17. The control framework reveals an unusual pattern of BGP route flapping originating from a specific peer. Network telemetry indicates a sudden increase in BGP update messages and a corresponding degradation in network convergence times. Initial investigation suggests a potential security compromise or misconfiguration impacting the BGP session with this peer. The network engineer must determine the most appropriate immediate course of action to restore stability and mitigate potential risks. Option A. Immediately disable BGP authentication with the affected peer to restore session stability and allow for further investigation without immediate disruption. Option B. Initiate a full rollback of all recent BGP configuration changes across the network to revert to a known stable state. Option C. Implement a temporary rate limiting policy on BGP update messages from the affected peer while simultaneously gathering detailed BGP state information and logs for analysis. Option D. Rely solely on external threat intelligence feeds to identify the nature of the attack, and then apply generic mitigation strategies. The correct answer is A. Immediately disable BGP authentication with the affected peer to restore session stability and allow for further investigation without immediate disruption. Explanation. The control framework reveals a critical juncture in network security and operational integrity. The challenge lies in balancing the immediate need for network stability and performance with the long-term implications of security vulnerabilities and potential compliance breaches. A misstep in this scenario could lead to significant service disruptions, data compromise, and regulatory penalties, making a thorough understanding of the underlying protocols and their security implications paramount. The correct approach represents best professional practice because it prioritizes a systematic, evidence-based resolution that adheres to established security principles and Cisco's recommended best practices for ENARSI. By isolating the issue, gathering detailed telemetry, and applying a phased remediation strategy, the network engineer ensures that the fix is not only effective, but also minimizes collateral impact. This aligns with the principle of least privilege and defense in depth, crucial for maintaining a secure and resilient enterprise network. Furthermore, this methodical approach facilitates accurate documentation and post-incident analysis, which are vital for continuous improvement and audit readiness. An incorrect approach that involves immediately disabling BGP authentication without a full understanding of the attack vector or the potential exposure is professionally unacceptable. This action would create a significant security gap, potentially exposing the network to further manipulation or denial of service attacks. It bypasses fundamental security controls and demonstrates a lack of due diligence, violating the ethical obligation to protect network resources and data. Another incorrect approach, such as solely relying on external threat intelligence without internal validation, is also professionally deficient. While threat intelligence is valuable, it must be correlated with internal network behavior. Acting solely on external data without verifying its applicability to the specific network environment can lead to misdiagnosis and ineffective remediation, wasting valuable time and resources. This can also lead to unnecessary network changes that might introduce new problems. Finally, an approach that involves a broad, uncoordinated rollback of recent configuration changes without precise identification of the root cause is professionally unsound. While rollbacks can be a recovery tool, an indiscriminate rollback can disrupt legitimate functionalities, cause further instability, and obscure the actual problem, making future troubleshooting more difficult. It lacks the analytical rigor required for effective incident response and demonstrates a reactive, rather than a proactive problem-solving methodology. Professional decision-making in such situations requires a structured incident response plan, a deep understanding of the protocols involved in this case, BGP and its security features, and a commitment to evidence-based troubleshooting. It involves prioritizing actions based on risk assessment, impact analysis, and adherence to security best practices and organizational policies. Question 18. The risk matrix shows a high probability of network instability if BGP path selection attributes are modified without proper validation. A network engineer is tasked with implementing a new BGP policy to prefer a specific transit provider based on a combination of local preference and MED values. What is the most professional and risk-averse approach to implementing this change across a multi-homed enterprise network? Option A. Configure the BGP attribute changes on all edge routers and then reboot each router sequentially to apply the new configuration. Option B. Immediately apply the BGP attribute changes to all edge routers simultaneously to ensure consistent policy application across the network. Option C. Implement the BGP attribute changes on a single edge router first, monitor its behavior, and then incrementally apply the changes to other edge routers with a predefined rollback plan in place. Option D. Implement the BGP attribute changes on a subset of edge routers, and then wait for a full business cycle to observe the impact before proceeding with the remaining routers. The correct answer is C. Implement the BGP attribute changes on a single edge router first, monitor its behavior, and then incrementally apply the changes to other edge routers with a predefined rollback plan in place. Explanation: this scenario presents a professional challenge due to the critical nature of network stability and the potential for cascading failures impacting business operations. The need to implement a complex routing protocol change requires careful planning, thorough testing, and a deep understanding of the protocol's behavior under various conditions. The primary regulatory framework to consider for this exam is the Cisco ENARSI syllabus itself, which implicitly guides best practices for implementing advanced routing services within an enterprise network. There are no external, specific US or UK regulations directly dictating the technical implementation of BGP path selection attributes for this scenario, but the underlying principle of ensuring network reliability and security, which is a general business and IT governance expectation, is paramount. The correct approach represents best professional practice because it prioritizes a phased, controlled rollout of the BGP configuration change. This involves meticulous pre-configuration validation, a staged deployment across different network segments, and robust post-implementation monitoring. This methodical process minimizes the risk of widespread disruption and allows for rapid rollback if unforeseen issues arise. This aligns with the ENARSI exam's focus on implementing and troubleshooting advanced routing, emphasizing a practical, risk-aware methodology. The professional justification lies in upholding the integrity and availability of the enterprise network, a core responsibility of network engineers. An incorrect approach that involves immediately applying the BGP attribute changes to all edge routers without prior testing or a staged rollout is professionally unacceptable. This would be a reckless disregard for network stability, potentially leading to significant downtime and business impact. While not a direct violation of a specific US or UK law, it represents a severe breach of professional responsibility and IT governance principles, which expect due diligence and risk mitigation. Another incorrect approach, such as relying solely on vendor documentation without understanding the specific network context and potential interactions with existing configurations, is also professionally deficient. This demonstrates a lack of critical thinking and an over-reliance on external guidance without proper validation, increasing the likelihood of unintended consequences. Finally, an approach that neglects to establish clear rollback procedures before implementing the changes is a critical oversight. This leaves the network vulnerable in case of failure, demonstrating poor planning and a failure to adequately prepare for contingencies, which is a hallmark of unprofessional network management. The professional decision-making process for similar situations should involve a comprehensive risk assessment, detailed planning of the change, thorough testing in a lab environment, a phased deployment strategy with clear rollback plans, and continuous monitoring throughout and after the implementation. This structured approach ensures that technical changes are implemented effectively while safeguarding network stability and business continuity. Question 19. The evaluation methodology shows a network engineer responsible for selecting and implementing a new interior gateway routing protocol for a large, multi-site enterprise network. The primary goals are to achieve rapid convergence during network changes, ensure scalability as the network grows, and maintain a manageable operational overhead. The engineer is considering protocols that are commonly discussed and implemented in enterprise environments, with a focus on those that offer advanced features for traffic engineering and route manipulation. Which of the following approaches best aligns with the requirements of implementing advanced routing services in an enterprise network, as emphasized by the ENARSI curriculum? Option A. Implement a proprietary routing protocol that offers unique features not found in standard protocols, with the expectation that it will provide a competitive advantage in network performance. Option B. Focus on a protocol that is primarily designed for small to medium-sized networks, as its simpler state management will reduce the likelihood of configuration errors, even if it means sacrificing some scalability. Option C. Prioritize a link state routing protocol known for its fast convergence and hierarchical design capabilities, and leverage its advanced features for route summarization and inter-area communication to manage network complexity and optimize traffic flow. Option D. Select a simple distance vector protocol that is easy to configure and has a low administrative overhead, assuming that rapid convergence is not a critical requirement for the majority of network segments. The correct answer is C. Prioritize a link state routing protocol known for its fast convergence and hierarchical design capabilities, and leverage its advanced features for route summarization and inter-area communication to manage network complexity and optimize traffic flow. Explanation. The evaluation methodology shows a scenario where a network administrator is tasked with implementing a new routing protocol to improve network convergence and efficiency within an enterprise network. The challenge lies in selecting the most appropriate protocol that balances performance, scalability, and operational complexity, while also adhering to best practices for enterprise network design and security. The administrator must consider the existing network infrastructure, the potential impact on existing services, and the long-term strategic goals of the organization. The correct approach involves a thorough comparative analysis of routing protocols based on their technical characteristics, operational overhead, and compatibility with the Cisco ENARSI curriculum's focus on advanced routing services. This includes understanding the nuances of link state versus distance vector protocols, their convergence times, scalability limitations, and security implications. Selecting a protocol that aligns with the exam's emphasis on OSPF and IGAP, and understanding their advanced features like route summarization, redistribution, and path selection represents best professional practice. This ensures the implemented solution is robust, efficient, and aligns with industry standards taught in the ENARSI certification. An incorrect approach would be to select a protocol based solely on perceived ease of implementation, without considering its long-term implications or its suitability for an enterprise environment. For instance, choosing a protocol with known scalability issues for a growing network would be a significant professional failure, leading to performance degradation and increased operational costs. Another incorrect approach would be to implement a protocol without proper security considerations, such as neglecting authentication mechanisms, which exposes the network to potential routing manipulation and denial-of-service attacks. Furthermore, selecting a protocol that is not covered in depth by the ENARSI curriculum might indicate a lack of understanding of the core competencies the certification aims to validate, potentially leading to suboptimal design choices and difficulty in troubleshooting. Professionals should approach such decisions by first defining clear requirements and objectives for the routing solution. This involves understanding the network's current state and future growth projections. Next, a comparative analysis of candidate protocols should be conducted, focusing on metrics relevant to the enterprise environment, such as convergence speed, scalability, administrative complexity, and security features. This analysis should be informed by the knowledge gained from relevant certifications like ENARSI, which provide a framework for understanding and evaluating advanced routing technologies. Finally, a pilot deployment or thorough lab testing should be performed before full implementation to validate the chosen protocol's performance and stability. Question 20. Operational review demonstrates that the enterprise's BGP peering configuration lacks robust security measures, potentially exposing the network to unauthorized route manipulation and access. Given the organization's commitment to maintaining a secure and compliant network infrastructure, what is the most appropriate technical approach to mitigate these risks? Option A. Configure BGP to accept peering requests from any source IP address, relying on routing policies for traffic filtering. Option B. Utilize access control lists, ACL, to permit BGP traffic only from known peer IP addresses without cryptographic authentication. Option C. Enable BGP without any authentication mechanism, assuming internal network security is sufficient. Option D. Implement MD5 or SHA 256 keyed hash authentication for all BGP peering sessions. The correct answer is D. Implement MD5 or SHA 256 keyed hash authentication for all BGP peering sessions. Explanation. Scenario analysis. This scenario presents a common challenge in enterprise networking where the implementation of advanced routing protocols, specifically BGP, must align with evolving security and operational compliance mandates. The challenge lies in balancing the technical requirements for efficient routing with the imperative to prevent unauthorized network access and data exfiltration, all within the context of a specific regulatory framework that dictates acceptable network security practices. The need for robust authentication and authorization mechanisms for BGP peering is paramount, as misconfigurations or vulnerabilities can lead to significant security breaches and operational disruptions. Correct approach analysis. The correct approach involves implementing BGP authentication using MD5 or SHA 256 keyed hash authentication between peering routers. This aligns with the principles of network security and data integrity, which are implicitly or explicitly required by most regulatory frameworks governing enterprise IT infrastructure. By ensuring that only authorized peers can establish BGP sessions, the network operator prevents malicious actors from injecting false routing information, route injection, or hijacking existing routes. This directly addresses the risk of unauthorized network access and manipulation, thereby upholding the integrity and availability of network services. Such a practice is a fundamental tenet of secure network design and operation, often a prerequisite for compliance with data protection and cybersecurity regulations. Incorrect approaches analysis. Implementing BGP without any authentication mechanism is a significant regulatory and ethical failure. It leaves the network vulnerable to route injection and hijacking attacks, which can lead to denial-of-service conditions, unauthorized access to sensitive data, and misdirection of traffic. This directly violates the principle of maintaining a secure and reliable network infrastructure, which is a cornerstone of most compliance standards. Configuring BGP to accept peering requests from any source IP address, even with a strong routing policy in place, is also a failure. While routing policies can filter traffic, they do not prevent the establishment of unauthorized peering sessions. This creates an unnecessary attack surface, as a malicious entity could attempt to establish a BGP session and then exploit potential weaknesses in the routing policy or other network devices. This approach fails to implement a fundamental security control at the peering level. Relying solely on access control lists, ACL, to permit BGP traffic from known peers, without implementing cryptographic authentication, is insufficient. ACLs can be bypassed or spoofed, and they do not provide a mechanism to verify the identity of the BGP speaker. While ACLs are a useful layer of defense, they are not a substitute for strong authentication in securing critical routing protocols like BGP. This approach lacks the necessary depth of security to meet modern compliance requirements for network integrity. Professional reasoning. Professionals must adopt a defense-in-depth strategy for network security, especially for critical protocols like BGP. The decision-making process should prioritize security controls that provide strong authentication and integrity checks. When implementing BGP, the primary consideration should be to secure the peering sessions against unauthorized access and manipulation. This involves understanding the specific security requirements mandated by the relevant regulatory framework and applying best practices that directly address those requirements. A thorough risk assessment should inform the choice of security mechanisms, ensuring that the implemented solutions are robust, verifiable, and maintainable. The professional's responsibility is to design and operate networks that are not only functional, but also secure and compliant, safeguarding the organization's data and services.